Hi class, welcome to the next section, chapter 7.2, the definite integral. There's a few different classifications of integrals, just like there is for derivatives. So here we're going to talk about what's called the definite integral. There's also what's called the indefinite integral and improper integrals, which improper integrals you would see in a calculus 2 course. Okay. So we're going to talk about the definite integral today. And really what we're going to do is we're going to start off by talking about how to find the area under a curve exactly and expanding that into our ideas of the ideas for calculus 2, which is the integral. Okay. So excuse me. Let's start off with the definition. So we'll really just review quite a bit of what we had last section in 7.1 so that it's fresh and ready for us to use for this section. Okay, so let's say that we have a function f that is defined over an interval from a to b, including the endpoints of this interval. And let's say that we divide this interval into n subintervals. Okay, so again, this should be reminiscent of us dividing this space into n rectangles, right? So what we're doing is we're dividing the length of a to b into n equal parts. Okay, each of those parts have a length of delta x, which is the distance between a and b minus a, divided by n. We're going to have a series of points on these intervals. The first one we'll call a, the last one we'll call b. This is the same, a is the same as x naught, and b is the same as xn. And then we'll label them increasing by integer values all the way until we get to the nth one. So x0, x1, x2, all the way to xn. So these are the endpoints of the intervals. These are where these intervals lie on the number line. Okay, we're going to have x1 star, x2 star, and x all the way up to xn star be any sample points inside of these intervals, meaning that x1 star lies anywhere between x0 and x1. x2 star lies anywhere between x1 and x2. x3 star lies anywhere between x2 and x3, and so forth and so forth. Okay. So again here, just to clarify this into a more rigorous notation, x sub I star is in the ith subinterval, right? So x1 is in the first interval, so anywhere between x0 and x1, etc., etc. So x I star is between the x value xi minus 1 and xi. Then the definite integral of f from a to b is given by this notation. Okay, so this is read as the integral from a to b of f of x with respect to x. Okay, so this is very, very important here. You're going to see this all throughout calculus 2. So again, here we're just kind of bridging the gap between calc 1 and calc 2. So the way that this is called a definite integral because it has bounds from a to b. But generally when we talk about this, we don't say I'm trying to calculate the definite integral. We just say I'm calculating the integral. But when it is bounded, right, when you're going from one number to another number, right, it is a definite integral. And this is equal to the limit as n goes to infinity, so getting really, 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 really small rectangles for our approximation for Riemann's sum. Here, we're taking any value in between the interval, this x sub I star. So it's not necessarily a left-hand interval or a right-hand interval, right-hand sum or left-hand sum, I'm sorry. We're taking the height of the rectangles to be any point within. So it could be at the left endpoint, at the right endpoint, or anywhere between those endpoints. Okay. So we said in the last section how the limit as n goes to infinity is equal to the actual area under the curve. This is the notation for that. It is the integral from a to b of our function f. It's the same as the actual area under the curve. So the limit of this Riemann sum approximation. Okay, so all of this to say as long as this limit actually exists, right? So any choice of sample point will give us the same value out if we take the limit to infinity, right? So it could be left-hand sum, right-hand sum, or anywhere in between, right? So if this does exist, then we say that our function is integrable over the interval a to b. Okay. Here we call a the lower bound. So again, as I was saying, we're bounded from a to b. These are my bounds. A is my lower bound. B is my upper bound. A and b are called together as a unit are called the bounds of integration. F of x is called the integrand. Okay. And this little dx informs us of which variable we're going to be integrating with respect to. Just like for our derivatives, we had the derivative with respect to x, or the derivative with respect to t, or whatever other variable it is that we're working with. Here, it does the same thing. It's the same thing as it is from integration. It is our differential, right? So remember from our unit on differentials and linear approximations that dx and delta x are the same thing. So when we put them in an integral, this delta x turns into the differential x. So when we are talking about area under a curve, okay, so before we just use this rectangle approximation. However, when we're actually considering it, anything that's above the x-axis and below the curve is positive, and anything that is between the function and below the x-axis is negative. Okay, so for instance, let's say that this is my parabola. So if we say, okay, the area under the curve, well, we know that this is the area under f and that this is the area under f. But for this part, does that mean that we're looking at all of this space? No. So we're always looking at the area between the x-axis and my function, right? So here, this is a positive value, positive area. Here, this is a negative area, even though, yes, it's true that area cannot be negative. In terms of integration, this is a negative area. And then this is also a positive area. So anything below the x-axis, the area between the x-axis and that function value is negative. Okay, so let's talk about another theorem. So let's say we have a function that's continuous on a closed interval, a to b. Okay, or let's say that f has only a finite number of jump discontinuities. Then we can say that our function is integrable on a to b. So in order for it to be integrable, it has to be continuous, or if it is jump discontinuous, that there's a limited number. Okay, so meaning there's not an infinite number of discontinuities within this interval a to b. Okay. So if it's integrable, then that means that the definite integral exists, right? So let's talk about some properties of sums, right? So we've done a few summations already. If you, again, have seen this stuff already from pre-calculus, then these properties should be familiar to you. There may be one or two that you haven't seen before, but we're not going to talk about how to find, for instance, the value of a partial sum or anything like that at this point. Okay, so let's say that I am summing together a constant value c, right? So remember, I is my index. There's no I in this notation here, right? Which means that I'm adding c together n times. I'm adding n c's, so c plus c plus c plus c plus c plus c until I get to whatever this ending index is, n. So remember what addition is. If you're adding the same thing over and over and over again, you're really just multiplying that constant by however many times you added it together, okay? Here, if I have a constant multiple of some sort of a function on the inside here, then you can pull out that common constant multiple. We saw that in the last section with our delta x, right? Our delta x is a common value, right? The size of the base of all of our rectangles, and so in the end product we can pull that out in our sums. So if I have a constant multiple of whatever my function form is here, this a sub I can pull out the c. Okay. Here, if I'm adding two different sort of index functions together, and I'm taking the sum of those, then I can separate that to two separate sums, right? So the sum of these a sub i's plus the sums of these b sub i's, where I is the counting index. If I am adding up I, right, so this is going to be 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 up to n, then that sum, which we call partial sum, has the form 1/2 n times n plus 1. If I am summing together I squares, so 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, etc., this has a closed form partial sum of 1/6 times n plus 1 times 2n plus 1. So if this was, let's say, up to 5, I would just replace 5 everywhere for n, and I could find that partial sum. Here, the nth partial sum of I cubed has the form of 1/2 n times n plus 1 squared. And that should make sense because it is, well, we're not going to get into it too much, but it's basically this one squared. Okay. So these are important formulas that we're going to use in this section. So 1 through 3 are just general properties of sums. 4, 5, and 6 are going to be specifically used for us to find these definite integrals, right? We're going to find definite integrals by taking the limits of these summation notations for right-hand or left-hand sums. All right. Next one. Okay. Remember, just like derivatives are really just limits, all the properties of derivatives came from the properties of limits. Since integrals are really just sums, okay, right? An integral is just a limit of a sum. All the properties that we have for integrals come from the properties of limits and the properties of sums. So anything that's shared between limits and sums will apply to integrals. Okay, so one of the main a very important one is the integral of a to b times c, or of c, right? A constant function is just c times b minus a, right? And this should kind of make sense if you think about it. What is a constant function? A constant function is just a line, right? It's the line that starts at a and ends at b. Well, what is the area of under a line, right? It is c, which is the height, and b minus a, which is the width. So it's just a rectangle, basically. Okay. Here, if I have a constant times a function, and I'm taking the integral from a to b, I can do the same thing as I did for my sums, and I can for limits, which is I can pull out the constant c. Okay. If I have the integral from a to b of a function f plus or minus a function g, then just like properties of limits, just like properties of sums, I can separate that into two separate integrals. So the integral of f from a to b plus or minus the integral of g from a to b. If I am going from one bound to the same bound, so from a to a, meaning that there is no distance horizontally, right? So if you think about that, like, what would the area be to approximate that, right? If I haven't moved to the left at all, if there's no base for my rectangle, there's no area to find. Okay. My integral from a to b of a function is the same as the integral from b to a, but negative. So if I switch these bounds, I have to switch the sign. Okay. So if I go from a to b in the positive direction, it's the same as if I go in the negative direction, as long as I change the sign. Okay. Here, if I go from a to b of a function, and then from b to c of my function, it's just like if I went from a to c. So this is an important one. This comes in pretty handy when I have really difficult functions to evaluate. I can break it down into smaller functions, smaller intervals where it's easier to look at it in pieces. If my function is always positive or 0 over my interval, then my integral has to always be positive, right? So if my function is always 0, then there's no rectangles, my area will always be 0. If my function is always positive, then the area always has to be positive because the area is always above the x-axis, right? If my function f is always larger than g over an interval, then the integral of f is always going to be larger than the integral of g, right? The area under f will always be larger than the area under g if f is always the larger function, okay? Here, if I can bound my function by a lower value and an upper value, meaning that I know that my function f is always between 2 and 10, for instance, over this interval, then my integral, my area, can also be bounded. Okay. So this brings us, so there's a lot of rules here. Okay. You'll become very familiar with them, don't worry about it. We have what's called a midpoint rule. So we've covered the left-hand rule, we've covered the right-hand rule, the right-hand side approximation, the left-hand side approximation. We have what's called a midpoint approximation as well, where instead of using the left or right endpoints for our rectangles, we take the midpoint, the value right in between the two. Now, there's actually several different types of Riemann sum approximations, the left-hand sum, the right-hand sum. Now we have the midpoint rule, and there's actually 2 more that we have that we cover in a Calculus 2 course that we're not going to cover here. Okay, but let's talk more about the midpoint rule. So my integral from a to b of f of x is approximately equal to the sum of the midpoints, right? So here, taking rectangles where the height of the rectangle is given by the midpoint between those subintervals, between x naught. So for instance, in the first rectangle, between x naught and x1, I would take the value right in between those two to give the height of my rectangle approximation, right? So if we expand this sum, this is what our notation would look like, right? So here, delta x is b minus a over n. xi bar is the halfway point between xi minus 1 and xi, right? So let's say I was looking for the third value. It would be the midpoint between the second and fourth endpoints, right? So that's how that works. So it's the midpoint of the subinterval xi minus 1 and xi. So let's go ahead and do an example with the midpoint rule. So let's say that we're approximating the area under the curve. F of x equals x cubed minus 3x squared from x equals 0 to x equals 1 using the midpoint rule, the right hand sum, and the left hand sum with n equals 4. So we're going to take this function and we're going to do 3 approximations. Okay. Now, one thing I want to say real quick about the midpoint rule. So if you notice, I didn't give you guys a graph for this, which is fine. You guys have seen it for the left hand and right hand sum. You know how to calculate these things. But if you're interested in what the midpoint rule looks like, especially depending again on the concavity, whether we're increasing and decreasing, generally what happens with the midpoint rule sums is that half of our rectangle approximation, for any one rectangle, half of it would be an underestimate and half of it would be an overestimate. So it kind of averages out to be really, really accurate. So the midpoint rule generally is much more accurate than the left-hand sum or right-hand sum, right? So for instance, let's say our right-hand sum is an over approximation. Our left-hand sum will probably be an under approximation. And the midpoint rule would be right in between the two, because since all of the heights of the rectangles are the midpoints between these two, half of it is an over approximation, the other half is an under approximation. So it's generally much, much more accurate than either one of these two. So let's go ahead and check this out. We're going to look at x cubed minus 3x squared. We're going to go from 0 to 1. Okay, so we're over a very small interval. We're going to break that down into 4 pieces. Okay, we want to find the actual error in our estimates by calculating this area exactly. And the way we're going to calculate this exactly is by using the limit as n goes to infinity. Okay, by using this. So we're going to find the exact area using this limit form, and we're going to compare our approximations and check their errors. So here we know delta x is 1 over 4 because I'm going from 0 to 1, and I'm breaking that into 4 equal pieces. Now that we know what delta x is, let's find all of our x values. Obviously, we know x naught is 0, and x4 is going to be 1, so we got to find the values in between. So we're just counting by 1/4, right? So we got 0, we have 1/4, we'll have 1/2, we'll have 3/4, and we will have 1. So those are our 5 values that we break our point down to. If we look at the midpoint rule, all the rules are the same. They all work the same way. It's just what value am I evaluating my function at. The midpoint rule says I look at the value right in the middle between x0 and x1 for my x1 star. The value right in between x1 and x2 for my x2 bar. The value right in between x2 and x3 for my x3 bar, and the value right in between x3 and x4 for my 4th point. So let's find those midpoints. We can either look right in between these and go, oh, I know that halfway between 0 and 1/4 is 1/8, but maybe we don't know how to do that exactly, right? So we do have a formula. You can add these 2 points together and divide them in half, right? Now we can do that again. We can go x1 plus x2 and divide it in half, or our delta x is still the same. It's still 1/4. So, right, look at this notation. It's still, everything is still times delta x here. Okay, the delta x doesn't change. So now that I found my first value, I could just take 1/8 and just add 1/4 to it, and then 1/4 to it again, and then again, and then again until I get my 4. So there's 2 ways to do this. Find your first value, and from there, just add delta x to it again and again and again. Or you can continue to use the definition of a midpoint of your 2 endpoints of your subinterval, right? So for the next one, x2 bar, I can add these 2 together and divide them in half, okay? Or I can take 1/8 and I can add to it 1/4. I'll get the same thing. So 1/4 plus 1/8 is 3/4. Okay, I'm sorry, 3/8. Okay, because I have to turn this into 2 over 8 and add that to 1 over 8. That's 3/8. So if I do the midpoint formula, okay, I get 2/4. So that turns into 3/4 times 1/2 is 3/8. So you see, no matter which way I approach it, I get the same answer. So the midpoint method, right, by finding the midpoint between the 2 subintervals, I get 3/8. Or if I just took 1/8 and I add to that 1/4, I still get 3/8. It doesn't really matter. So I can take 3/8 and I can add 1/4 to this value to get my next one. Or if we continue with this, we can just take the average value between the 2 ends, between x2 and x3 here, and get 5/8. If I add another 1/4, you can kind of see that there's already a pattern, right? It's going up by 2, so this next one will be 7/8. Okay, so it's actually really easy to find these values. So I have my values. So now that I have the values for my midpoint rule that I have to plug in, I have to actually plug these in. So I'm going to evaluate f at 1/8. I'll evaluate f of x at 3/8. I'll evaluate it at 5/8. I'll evaluate it at 7/8. I'll add them all together and then multiply times 1/4, right? So following the rule here, delta x times f of x1 bar plus f of x2 bar and so forth, right? So as I showed you before, another way of finding this is to just continue to add delta x to your previous value that you had before. Okay, that's all that this one says. So my area is approximately equal to 1/4, my delta x, times my x bars, xi bars, being plugged into my function. So if I actually give you the values here, I have 1/4 times negative 23 over 512 minus 189 over 512, minus 475 over 512, minus 833 over 512. All have a common denominator. So this comes out to 95 over 128 negative. And now that we have an exact value, we can give the decimal approximation, which is negative 0.74211875. So if you notice here, I kept more than the 4. I gave 7 digits because when we're doing approximations of this manner, especially if we're checking it against the exact solution, we can get very, very close to the actual answer. So we want to keep more decimals of accuracy when we give our answers here. Okay. Now let's do the right-hand side. The nice thing is I already have all my x values. So right-hand side means I don't evaluate x naught, but I do x1, x2, x3, and x4. Okay. So right-hand side. So I'm going to have 1/4, and then not the first term, which is 0, but all the other terms after it. Okay, up until the last one. So this will be 1/4. I plug in 1/4 into my cubic that I have. I get negative 11 over 64, minus 5/8, minus 81 over 64, minus 2. Add those together, I get negative 65 over 64, which is approximately negative 1.015625. Now when I do the left-hand side, it's almost identical, except that instead of having F1, this goes away, these 3 stay, and then I include F of 0. So going from the right-hand sum to left-hand sum is easy. You just take one off and then do one extra calculation. And as long as you have all your previous values, you can just find it, right? So we have 1/4. F of 0 is 0. And then I have negative 1164, negative 5/8, negative 8164. And that's it, because this last one is not included in the left-hand sum. Plug all these in, and I get negative 33 over 64. So we have negative 0.515625. So if you notice, this is about 3/4. This is about 1, and this is about 1/2, right? So they each differ by about 0.25, just about. Okay. So now we have to compare this to the exact value. So at this point, I have not shown you guys how to evaluate a definite integral. So you cannot use any methods if you already know them in order to evaluate at this point, right? So at this point in time, you need to use this limit form definition. And on your final exam, I will ask you to specifically use this limit form. If I don't specifically ask you to use this limit form, then you can feel free to use any other method that you have for evaluating an integral, which is what we will go over in the next 2 sections, is how to evaluate integrals without having to do limits or approximations. So I have my midpoint rule, my right-hand side, and my left-hand side approximations. So let's find the exact form. So we want the exact area under x cubed minus 3x squared from 0 to 1. And we can find this by finding the integral from 0 to 1 of x cubed minus 3x squared. Okay. So in order to do this, we need to take our integral and we need to form it into our sum. So the integrand form stays the same, this x cubed minus 3x squared. We know this dx turns into delta x. This integral sign gets replaced with the summation sign, and our starting index is 0 and our ending index is 1. Okay. Well, actually is n, because we want to break this down into an infinite number of rectangles, right? So we want to rewrite this as a summation. We can use our properties of integrals first, right? So properties of integrals are the same as a property of limits and properties of sums, which is that we can break this down because this is 2 functions being added together or subtracted. So we can break those into 2 separate integrals. Here you see we have a constant multiple, so we can pull that out as well. And now we can focus on this x cubed and this x squared, which is good because if you look at what I gave you way in the beginning for properties of summations, I told you how to find the sum of an I squared, where that's our index, and a sum of I cubed, where that's our index, and a closed form formula for those. Okay, so let's finish turning these integrals into sums so that we can use the property of sums and take their limit as n goes to infinity. So I have my x cubed minus 3 integral of x squared. This integral gets replaced with the limit sum, right? This integral gets replaced with the limit sum. My starting index is 1, and I go up to n. So remember, it doesn't really matter if I start at 0 or if I start at n. The definition that I gave you, I believe we start with 1, so we're really just following the formula. The definition, right? Our definition here is from 1 to n, so I just replace this integral with the limit sum. The function that's inside of the integral is the same function that's inside of my summation. This dx turns into delta x, right? So there's like a part for part transformation. The integral is the limit sum. The function is the function, but in terms of I, right? So xi is into my function. The dx is the delta x. All right. So here we go. Okay. Limit sum 1 to n. Limit sum 1 to n. X cubed is xi cubed, right? I'm plugging in x1, x2, x3, x4, x5, so forth and so forth into this x cubed function, into this x squared function from here that I pulled out. It's the same thing, so I start from 1 all the way to n, but I want n to go to infinity, right? My delta x is 1 over n because this is from the length here is 0 to 1, and I'm going to divide it into n pieces, but n is going to go to infinity, right? So the bounds here are 0 to 1, that's the length, so b minus a over n. X naught in this case is 0. X1 is 1 over n. X2 is 2 over n, and then 3 over n, 4 over n, to I over n, forever and ever, right? Because n is going to go into infinity, right? So I can now replace this integral with this limit sum, which I've already done. So all I've done right here is just rewrite what I had at this point, at this time. I'm going to replace my delta x with the form that I have, which is 1 over n. Okay. And all of these x's, right, this xi cubed is really just I over n. Each x sub I, right, because that's what my formula is, xi squared xi cubed, each x sub I is just I over n. So I followed the pattern. The first one is 0, the next one is 1 over n, the next one is 1 over n plus another 1 over n, so 2n, and then the next one is 3n and then 4n. The pattern is that each x sub I is I over n. So my xi, which is xi squared, and xi cubed, I take this, I have this form. So everywhere I see xi, I replace with 1 over n, and everywhere I see delta x, I replace with 1 over n. Okay, so I have I over n cubed, because xi is I over n. Delta x is 1 over n. Xi is I over n, so that's I over n squared, and delta x is 1 over n. So now I can start to simplify these, right? It's very clear that I have this 1 over n. I could pull out as a constant, but if you notice what's going on here, well, this is I over n, and this is 1 over n. So let's pull out this constant of 1 over n. Actually, we can move this n's over, and we'll keep the i's, right? So I'm going to write the i's as a cube and a square because of the closed form formula I have for I squared and I cubed in terms of a sum. I squared and I cubed. I have a closed form for those. So my goal is to get i's to look like that inside of my integral. Let's go back. Oops. Okay. So what I do is the I gets cubed, the n gets cubed. I take the n out because I would like to pull it out as constants if I can. Plus n is going to go to infinity, so I would like to have those separated from the i's. So now that I have the i's in the form that I want, I would like to turn them into n's, right? Because my summations for I cubed and I squared was based on n. So I'm going to replace I cubed with the form that I have for its partial sum, and this I squared is going to be replaced with the formula I have, which I just showed you a couple times ago. So here I can pull out the n terms, okay? These are constants. They're not constants, but they're going to go with the limits, right? So I'm going to pull out these things so I can get these I cubes and I squares as sums isolated, right? I'm just isolating these things so I can replace them with their formulas. So the sum from I to n of I cubed, I know has this form, and the sum from 1 to n of I squared has this form, okay? So I replace it with this form. Now everything is in terms of n, and I'm taking the limit as n goes to infinity, which is what I need if I need to take a limit. So I'm going to try to work this n fourth back in here and this n cubed back here if I can. If I can't, then that's fine. Here, however, I do have a 1/4, so I would like to pull that out as a constant, right? Because I have the 1/2 n squared, n plus 1 squared. So if I can pull this out as a 1/4, same thing here. This is 3/6, so this is a 1/2. So if I can pull out that constant, that would be nice as well. But it looks like I didn't do that, but I am starting to simplify, right? Here I have an n squared over an n fourth, so that puts it over an n squared. Then I have this n plus 1 squared on top. This fourth looks like it's getting ready to move out because I simplified it as well. Here this 3/6 is starting to get ready to move out. And then n over n cubed leaves me with an n squared. I multiply out my numerator and denominator. Okay, I could have pulled out this 1/4 and 1/2, but it looks like I'm waiting for some reason. And now I can take my limit as I go to infinity, right? So here I know what happens. These go to infinity at the same rate. So this whole term just goes to 1/4. Here, leading term is n squared, leading term is n squared. So this just turns into the ratio of the coefficients, which is 1. So this turns into 1/4 minus 1, okay, which gives me a negative 3/4. So the exact value is negative 3/4 or negative 0.75, which is nice when we want to approximate. So our errors are as follows, right? The left-hand side was negative 0.515625, right? So around 1/2. So if we take the exact value minus our approximation, we have an error of around 25%. Okay, it's an underestimate. Our right-hand side is negative 0.75, and this was around 1, right? So also an error of around 25%. Okay, so that's an overestimate. And then our midpoint rule was very, very close. Look how much closer that is, right? It's accurate to 2 decimal places. So this was very, very close here. Very small error. Okay, also an underestimate because it was negative. So notice that the error in the midpoint approximation is much smaller than either the left-hand side or the right-hand side, right? So this is about 25, not 25% off, but you know, a value of 0.25 almost. So if we found the ratio between these two, it's much, much, much smaller. This is much more accurate than previous.